Hi, I'm Honson, an embedded software engineer at Latent AI. I'm here today to tell you about our flagship product, the Latent AI Efficient Inference Platform, or LEIP. LEIP is a machine learning ops SDK that can train, optimize, deploy, and secure neural network runtimes using any model and hardware. It's a unified SDK built specifically for machine learning engineers and software developers. In this video, I'll be walking you through an end-to-end workflow with the LEIP recipe, which includes training, hardware-specific optimization, testing, and deployment. For more detailed tutorials, refer to the LEIP SDK documentation linked below. So, what is a recipe and how do we use it? The LEIP SDK includes pre-configured but customizable templates called recipes that let you develop and deploy models to common hardware quickly with the best possible results. To us, a recipe answers questions like, how do I train a Yolo model on the MSCOCO dataset and run it on the Raspberry Pi? With LEIP, our recipes come with the ability to bring your own data, or BYOD. One of the first entry points into the LEIP SDK is through application frameworks, a tool which allows you to select from a series of machine learning backbones to train, all from the CLI. The machine learning components of these recipes are packaged modularly, enabling models, datasets, optimization schemes, and deployment targets to be swapped easily. What that means is that it's as trivial to train a model and optimize for a Raspberry Pi as it is for a NVIDIA Jetson AGX or a Samsung Galaxy. Today, we'll walk you through a classification recipe to optimize and deploy a GERNet backbone trained on open image class datasets into a Raspberry Pi. Let's get started. The first step to using LEIP is installing it. LEIP is provided as a convenient Docker container, which includes all necessary libraries and dependencies needed for your target hardware. As of this current recording, our current options are as follows: CPU only, CPU and CUDA optimized. For those who are interested in trying out multiple hardware platforms, I suggest using the CUDA optimized Docker image, since it supports the most amount of hardware, including x86 and ARM, both in the CPU, GPU, and TensorRT context. As of this current recording, we are on LEIP version 2.7.3. So we'll first log into the Docker registry via the docker login command. And then we'll Docker pull the image. Feel free to pause this video as your copy of the SDK is downloading to your system. Once your image is downloaded, next, we're going to import our license key. To do this, simply export a system variable as shown. Next, Docker run the image. You should be greeted with a bash shell under the root user waiting for instructions. You can verify the copy of the LEIP SDK is activated by simply typing in LEIP once you log into the screen. If your returning message does not indicate it's a missing license key, you're good to go. We are now ready to get started with training and exporting our model via application frameworks. Next, we're going to pull in a dataset from the LEIP Zoo. If you wish to bring your own data, feel free to refer to the BYOD section of the LEIP Recipes documentation, which was linked in the previous section of this video. Moving along, let's first download our eval and training datasets. Next, we will pass in a config file listing our values for the training process. This config file can be modified to suit your needs, but for our demo, we will use the defaults. We'll choose the GERNet model backbone and also hard code our checkpoint path to simplify finding the file later. Feel free to pause the video here until your training is done. To go over the command, we are using application frameworks, passing in the classifier recipe config, selecting our backbone, and also hard coding our checkpoint path here and providing the command train. Next, we'll export our model to a .pt file for use. We'll export the path of the checkpoint to declutter the following commands. From this point, you'll have multiple options before exporting your model. The first option is to evaluate the checkpoint against the evaluation set on the current machine. This will return to you the accuracy. Another available option is the predict command, which will run through the dataset and save the prediction results and images to a directory for viewing. To do this, simply change the command from evaluate to predict. Likewise, once you're completely satisfied with the evaluation results, simply run this command and export the model. Once we've exported our model, we can now focus on optimizing and compiling our model for our target hardware. First, I'll export the path of our model as a system variable to simplify the following commands. Next, we're going to use the LEIP pipeline command to quickly compile for floating point 32 and integer 8 for an ARM CPU target, such as the Raspberry Pi we're working with in this demo. To briefly go over this command, we're calling LEIP pipeline, which takes in 3 arguments: the input path, which is the .pt model above; the output path is where our model's artifacts will reside; and the config path, which is the YAML file that is required for the LEIP pipeline commands. While this is running, it's also important to note that the LEIP pipeline is simply a YAML file that can be modified and changed to run your own pipeline of commands. In our case, this YAML file we have passed will LEIP optimize our PyTorch model for int 8 inference, LEIP compile the PyTorch model for floating point 32, and also package both of these FP32 and int 8 variants of the model into their own respective LRE objects. Feel free to pause this video for the next steps after the LEIP pipeline is done running. Now that we have all of our compiled artifacts, we are now ready to evaluate and deploy our compiled model variants. For evaluation, we'll install a light server on the target hardware called the LRE Object Runner, also known as the LOR. We'll SCP this package over to the Pi, and then pip install the package. Now we'll SSH in. As you can see here, I'm on the Pi. We will then pip install. If this is your first time installing, gRPC might take some time to build. This is normal, but once the LOR is finished, we can run the LOR as such. Feel free to pass the debug flag to print out logging information, such as when the LRE object is received, when inferences are occurring on the target, as well as when they finish. Leave this running in the background, and we can return to our SDK. Now we're ready to evaluate. As a reminder, the evaluation command that we have used in application frameworks was evaluating the PyTorch model checkpoint. With this evaluate command, we are sending our packaged LRE object containing our model to the Pi. Here, we'll use the LEIP evaluate command, which passes in the following parameters: the input path of the directory holding the package, the test path, which is just the file containing the class names, labels, and such, our host IP address, which is the IP address of the Raspberry Pi itself, as well as the default port of the LOR, which is 50051. Now that this is sending, we'll switch back over to our Raspberry Pi and we'll check the logging information just to see it send over. As you can see, the model is extracting and activating right now. We have inference running. As we can see on the LEIP eval side, we are running inference over the dataset that we have provided. If you're satisfied with the compiled model, we can now deploy the artifact to the target hardware. To do so, simply cd into the workspace directory, run our packaging script, and pass the backbone and target architecture used. Once this is done packaging into a tarball, send this tarball to the target device. We can now head on over to the Pi to see some deployment examples once we SCP this. Now that the tarball is on our Pi, let's extract it. Inside, you'll see a Python and C++ example shown once we change directories into there. In our demo, we'll show a Python example and how to use our new artifact. For convenience, I'll export the float32 package paths as well as the int8 path. Before we run our last example, I want to show you what's inside the infer.py script. You'll notice that inside the script, the main component is simply a couple of lines where we import the object, give it data, and call an inference function. Pretty much right here in the highlighted area. Let's try it out now. And that concludes today's demo. With the help of LRE objects, developers can focus more on the application they're building and less on the nitty-gritty details of optimization and deployment. You deal with one object that has the ability to be replaced without tampering with the rest of your application. Furthermore, each LRE object is packaged with its own environment, so there's a separation of dependencies between the model itself and the application, allowing for robust modularity and hot swapping. LEIP Recipes help you create highly optimized models for the edge, with great runtime support to easily integrate into your applications and enable you to create robust, repeatable, and reproducible models. Given all these advantages, LEIP Recipes can accelerate your time to market for edge deployments by 10x. Looking at the bigger picture, LEIP Recipes can help you scale as an organization. We are actively working on adding new recipes, including numerous recipes for microcontrollers. If you want to reduce your bill of materials, fit multiple models into a single target hardware, and accelerate your time to market for edge AI deployment, we'd love to help. Contact us at info@latentai.com and stay tuned for more video tutorials coming soon. Until next time, see you around.